In the pantheon of global energy, light sweet crude is the celebrity. It is easy to refine, flows like water, and trades at a premium on the world stage. It is the champagne of fossil fuels. But lurking in the shadow of this liquid gold is its darker, denser, and far more complex cousin known as heavy crude. To the uninitiated, heavy crude is simply dirty oil. To the chemist, the geologist, and the engineer, it is a fascinating paradox. It is a substance that should technologically be producible, yet it accounts for a staggering portion of the world's remaining hydrocarbon reserves. It is a fuel that requires more energy to extract than any other, yet it powers the heavy diesel engines that move the global economy. It is a material so viscous it can be walked upon in cold weather, yet it can be broken down into the lightest, most volatile jet fuels. Today on Fun Facts Online, we are conducting a deep exploration into the molecular soul of the world's thickest fuel. We will journey from the microscopic van der Waals forces binding asphaltene sheets together to the macroscopic megaprojects in the boreal forests of Canada and the tropical belts of Venezuela. We will uncover the deep-time geological history that turned ancient marine life into modern bitumen, and we will examine the cutting-edge chemistry that is attempting to make this carbon-intensive giant compatible with a net-zero future. To understand heavy crude, one must first abandon the mental image of oil as a simple black liquid. Light crude is a cocktail of relatively small, simple molecules, mostly alkanes or straight chains of carbon and hydrogen, that slide past one another with ease. Heavy crude, by contrast, is a molecular mosh pit. Petroleum chemists analyze heavy oil using a method known as fractionation, which splits the crude into 4 distinct classes based on their solubility and polarity: saturates, aromatics, resins, and asphaltenes. The saturates are the good parts, the simple paraffins and alkanes that make excellent fuels. In light crude, they dominate. In heavy crude, they are the minority, often having been eaten away by bacteria over millions of years. Next are the aromatics. These molecules contain ring structures or benzene rings. They are denser and have higher boiling points. Heavy crude is rich in complex polycyclic aromatic hydrocarbons, which are known to be difficult to break down. Then we have the resins. These are the middlemen of the oil. They are polar, sticky molecules that act as a solvent for the heaviest fraction, the asphaltenes. Without resins, the asphaltenes would precipitate out of the oil and clog everything in sight. Finally, we arrive at the asphaltenes, the heart of darkness in heavy crude. Asphaltenes are not a single molecule but a solubility class, defined as anything that precipitates when you add a light solvent like N-pentane. They are massive, complex sheets of fused aromatic rings, stacked like a deck of cards, and riddled with impurities like sulfur, nitrogen, and oxygen. If crude oil were a body, asphaltenes would be the plaque in the arteries. They are the primary reason heavy oil is heavy. At a molecular level, asphaltenes aggregate. The flat aromatic sheets attract each other via pi-pi stacking forces, which are interactions between the electron clouds of the rings. They form nano-aggregates, which then clump into larger clusters. This structure creates a chaotic internal friction, resulting in high viscosity. In Canadian bitumen, the asphaltene content can reach 15 to 20%. In some Venezuelan extra-heavy crudes, it is even higher. These molecules are so large, with molecular weights in the thousands, that they do not boil. Instead, they char. If you heat them, they turn into solid coke or carbon, rather than vaporizing. This single chemical fact dictates the billions of dollars spent on coking refineries worldwide. Furthermore, heavy crude is not just hydrocarbons. It is a repository for heavy metals. The porphyrin structures within asphaltenes, which are similar to the heme in your blood or chlorophyll in plants, trap metal atoms. In heavy oil, these are predominantly nickel and vanadium. The vanadium content in Venezuelan Orinoco crude can be so high, over 400 parts per million, that the ash left over from burning it is considered a commercially viable source of vanadium mining. However, inside a refinery, these metals are poisons. They coat the expensive catalysts used to upgrade the oil, rendering them useless. Removing these metals is a chemical war of attrition. There is also the sulfur problem. Sweet oil has low sulfur, while sour oil has high sulfur. Heavy crude is almost universally sour. The sulfur atoms are not just floating freely, they are bound into the carbon rings. To remove them, you cannot simply filter them out. You must chemically break the ring and insert hydrogen to capture the sulfur as hydrogen sulfide, a deadly rotten egg-smelling gas. This requires massive amounts of hydrogen and high pressure, adding to the carbon footprint of processing heavy oil. But why does heavy oil exist in the first place? For decades, geologists debated whether it was immature oil that hadn't cooked long enough, or ruined oil. The verdict is now largely in. Heavy oil is the residue of a massive, subterranean crime scene. Most heavy oil started its life as conventional light oil. It migrated from deep source rocks into shallow, cool reservoirs, typically less than 80 degrees Celsius. In these cool, dark environments, it met an enemy: bacteria. Reservoirs like the Athabasca oil sands are essentially the world's largest compost heaps. Over millions of years, anaerobic bacteria and archaea feasted on the oil, but they are picky eaters. They prefer the light, easy-to-digest saturates. They eat the small molecules and leave the massive, complex asphaltenes and resins behind. This process is called biodegradation. The microbes eat the N-alkanes first, then the branched alkanes, and finally the simpler aromatics. What remains is a concentration of the indigestible components, the heavy, sulfur-rich, metal-laden molecules. The oil loses its hydrogen and gains density. As a byproduct of their feast, these microbes produce methane and organic acids known as naphthenic acids, which makes the resulting water in the reservoir toxic and corrosive. Alongside biodegradation, water washing occurs. Groundwater flowing past the oil reservoir dissolves the lighter, more soluble hydrocarbons, like benzene and toluene, carrying them away. This further concentrates the heavy, insoluble fraction. The result of this geological rotting is staggering. In Canada's Athabasca Basin, the biodegradation was so extensive that the oil became immobile. It is no longer a liquid. It is a semi-solid mixed with sand, known as bitumen. The Athabasca deposit alone contains more than 1.7 trillion barrels of oil in place. Even if only 10% is recoverable, it rivals the reserves of Saudi Arabia. But unlike Saudi oil, which shoots out of the ground under its own pressure, this oil is locked in a frozen embrace with the sand. While heavy oil is found worldwide, from California to Oman, two nations sit atop the lion's share: Canada and Venezuela. They are the twin giants of the heavy oil world, yet their geologies and challenges are distinct. Canada possesses the Athabasca oil sands, which is a hydrophilic or water-wet system. Imagine a grain of sand surrounded by a thin film of water, where the bitumen fills the void spaces between these water-wet grains. Because the sand is water-wet, the bitumen separates relatively easily using hot water. This is the basis of the famous Clark hot water extraction process developed in the 1920s. The challenge, however, is that the bitumen is incredibly viscous. It is essentially a hockey puck. At surface temperatures in a Canadian winter, it is hard as rock. In contrast, Venezuela holds the Orinoco Belt, the world's largest accumulation of liquid hydrocarbons. Unlike Canada, the sands here are often oil-wet, meaning the oil adheres directly to the rock. The advantage is that the reservoir is warmer, around 55 degrees Celsius, so the oil, while still extra heavy, is technically a fluid. It can flow, albeit very slowly, into a wellbore. This allows for cold, heavy oil production with sand in some areas. However, the oil is chemically more complex in terms of metals and acidity. Furthermore, political and economic instability has left much of the infrastructure to upgrade this crude in disrepair, forcing Venezuela to blend its heavy oil with lighter imported diluents just to move it. Speaking of moving it, let's look at the extraction engineering, which is truly an engineering of extremes. You don't drill for heavy oil in the traditional sense. You mine it or you steam it. In the shallow parts of the Athabasca Basin, where the oil is less than 75 meters deep, the method is brute force surface mining. The largest trucks in the world, the Caterpillar 797s, carry 400-ton loads of oil sand. The shovels have buckets large enough to scoop up a family garage. The sand is mined, crushed, and mixed with hot water in massive hydrotransport pipelines. As the slurry moves through the pipe, the bitumen separates from the sand. In separation vessels, the bitumen floats to the top as a black froth, while the sand sinks. The froth is then skimmed off, treated with solvents to remove water and clay, and sent to the upgrader. The clean sand and water are sent to tailings ponds, which are vast lakes where the fine clays settle over decades. However, for the 80% of reserves that are too deep to mine, the industry had to invent a way to melt the oil underground. This is where steam-assisted gravity drainage, or SAGD, comes in. SAGD is a feat of engineering elegance. Two horizontal wells are drilled, one 5 meters above the other, extending for kilometers through the reservoir. High-pressure steam is injected continuously into the upper well. The steam rises, forming a steam chamber that melts the bitumen. The viscosity drops from 1 million centipoise to 10 centipoise, effectively turning it into hot syrup. Gravity pulls the melted bitumen and condensed water down to the lower well, where it is pumped to the surface. This requires massive amounts of natural gas to boil water for steam. The steam-to-oil ratio is a critical economic metric. A ratio of 3 means you need 3 barrels of steam water equivalent to produce 1 barrel of oil. Another method is cyclic steam stimulation, also known as huff and puff. This involves injecting high-pressure steam into a well for weeks to fracture the rock and heat the oil, then shutting the well to let the heat soak, and finally opening the well to pump out the hot oil. Interestingly, in the 1950s during the Atoms for Peace era, a proposal known as Project Cauldron seriously considered detonating a 9-kiloton nuclear device underground in the oil sands. The theory was that the heat from the nuke would melt the bitumen instantly, creating a massive underground cavern of flowing oil. Thankfully, the idea was scrapped due to concerns about radiation and shockwaves cracking the caprock. Once you get heavy oil out of the ground, you have a physics problem. It doesn't want to move. Pipeline friction is the enemy. To move bitumen through a pipeline, you have two choices: heat it or dilute it. Most landlocked heavy oil is transported as dilbit, or diluted bitumen. The recipe involves taking 70% bitumen and mixing it with 30% diluent. The diluent is usually condensate, a very light hydrocarbon liquid like naphtha, that is a byproduct of natural gas processing. The result is a hybrid fluid that flows like a medium crude, but carries the chemical baggage of heavy oil. There is controversy surrounding this. When dilbit spills, it behaves differently than conventional crude. The light diluent evaporates rapidly, creating a toxic vapor cloud, leaving the heavy bitumen behind. If this happens in turbulent water, the bitumen can sink, making cleanup exponentially harder. In some regions, pipelines are insulated and heated to prevent the oil from turning into a gel that plugs the line. Finally, we must discuss refining, or cracking the carbon code. A refinery designed for light sweet crude cannot process heavy crude. If you fed bitumen into a standard distillation tower, the bottom 50% would just sit there as hot asphalt. To turn this sludge into gasoline, you need an upgrader or a deep conversion refinery. The goal is simple: increase the hydrogen to carbon ratio. Heavy oil has too much carbon and not enough hydrogen. You have two strategic choices: carbon rejection or hydrogen addition. Carbon rejection is often done via delayed coking. You heat the heavy residue to 500 degrees Celsius and dump it into a massive steel drum. The heat causes the long asphaltene chains to crack or break apart. The light vapors rise to the top and are captured to become diesel and gas. The heavy carbon atoms are left behind, fusing together to form solid petroleum coke, or petcoke. Petcoke is a coal-like solid, often piled in black mountains and sold as a cheap, high-sulfur fuel for cement kilns or power plants in Asia. It is the garbage of the heavy oil world: pure, concentrated carbon. The alternative is hydrogen addition, or hydrocracking. This is the elegant, expensive method. The heavy oil is mixed with hydrogen gas at extreme pressures of over 2000 psi and passed over a catalyst. The catalyst cuts the long carbon chains and instantly caps the broken ends with hydrogen atoms, preventing them from fusing into coke. It also rips the sulfur out of the rings, turning it into H2S. The result is more liquid volume and a cleaner, higher quality synthetic crude. But the cost of hydrogen and energy is immense. Economically, heavy oil always trades at a discount to light oil. This spread exists because refineries have to spend more money to process it, and because heavy oil is often landlocked or in politically difficult regions. Despite the cost and difficulty, the world needs heavy oil. Light sweet crude is excellent for making gasoline, but it is too light to make good heavy diesel or jet fuel in high quantities, and it produces almost no asphalt for road building. Complex refineries in the US Gulf Coast prefer heavy oil because they spent billions building cokers to handle it. The global refining system is a mix. It requires the bottom of the barrel to produce the full slate of products modern society demands. Looking to the future, the elephant in the room is carbon. Heavy oil has a significantly higher well-to-wheels carbon intensity than light oil. In a world moving toward net zero, the industry is betting on innovation. Solvent-assisted extraction involves injecting solvents like butane or propane along with steam to help dissolve the bitumen, cutting carbon emissions by 20 to 30%. There are also solvent-only methods like VAPEX being piloted to eliminate water use entirely. Furthermore, the heavy oil industry is a candidate for carbon capture, utilization, and storage. The upgraders and steam generators are massive stationary sources of CO2 that can be captured and injected back underground. Perhaps most intriguingly, researchers are investigating using asphaltene-rich bitumen as a feedstock for carbon fiber. The high carbon content and aromatic ring structures are chemically similar to the precursors used for high-strength carbon fibers. Imagine a future where heavy crude is mined not to produce gasoline, but to produce the lightweight materials needed for electric vehicles and wind turbines. Heavy crude is a testament to human persistence. It is a resource that geology tried to destroy, burying it in sand and letting bacteria eat away its energy. Yet, through chemistry and engineering, we have found a way to resurrect it. It remains a controversial fuel, anchoring energy security for some, while representing the most carbon-intensive liquid fuel for others. The story of heavy crude in the 21st century will not be about discovery, but about transformation. Can technology strip the carbon out efficiently enough to make it viable in a low-carbon world? Or will these trillions of barrels remain where nature intended, locked in the dark, cold sands, a geologic memory of ancient seas?